Let me show you how to be a good Bayesian.
Today, we are bridging the gap between cutting-edge Gaussian process research and the high-stakes world of industrial causal inference. My guest is Thomas Pinder, a senior data scientist in Netflix Studios team, building causal models to measure risk and vulnerability. Prior to this, Thomas was a senior applied scientist at Amazon working on Bayesian Synthetic Control methods and marketing mix modeling. He also spent time as a senior scientist in the maps team of Uber, where he built attribution models for Uber's core map technology. And honestly, Thomas has great tastes. Because he loves Gaussian processes. He loves them so much that he created the open source package GPJax. In this conversation, we dive deep into why Bayesian methods are essential for causal inference and decision making. We explore the why and the how of GPJax, the elegance of Bayesian synthetic control, and a fascinating new approach to synthetic difference in differences. We also get a sneak peek at Thomas's new project, Impulso, which aims to bring structural VAR models to the Python ecosystem. So if you like time series, you'll want to stick around. This is Learning Bayesian Statistics, episode 154, recorded March 17, 2026.
Let me show you how to be a good Bayesian. Change your predictions after taking information in. And if you're thinking I'll be less than amazing, let's adjust those expectations. What's a Bayesian? It's someone who cares about evidence.
Welcome to Learning Bayesian Statistics, a podcast about Bayesian inference, the methods, the projects, and the people who make it possible. I'm your host, Alex Andorra. You can follow me on Twitter at Alex_Andorra, like the country. For any info about the show, learnbayesstats.com is the place to be. Show notes, becoming a corporate sponsor, unlocking Bayesian merch, supporting the show on Patreon, everything is in there. That's learnbayesstats.com. If you're interested in one-on-one mentorship, online courses, or statistical consulting, feel free to reach out and book a call at topmate.io/Alex_Andorra. See you around, folks, and best Bayesian wishes to you all. Hello, my dear Bayesians. I just wanted to share that now the Learn Bayes Stats website has a blog section. So not only you will find articles about recent episodes we've done, or just some insights that we have about the episodes themselves, but also from time to time standalone blog posts. And for that first blog post, well, I actually wrote one about the coding agent skill that I wrote a few days ago, which is a Bayesian workflow coding agent skill. And in the blog post, I go through how I did it and how it only took mass producing the same mistakes 63 times to get there. So if you want to get the detail, the full breakdown, what surprised me about how LLMs knew Bayes or not, what also they were great at consistently and also not great at consistently, well, you should check out the blog post. In particular, that agent skill enforces the full Bayesian workflow, prior predictive checks, diagnostics, calibration, reporting, every single time using PrimeC and the all-new RVs 1.0, spearheaded by, among others, the brilliant Osvaldo Martin and Oriol Aureli-Pla, two friends of the show. Of course, this is an open source skill, so feel free to chime in with ideas, bug reports, PRs. It works with Cloud Code, Cursor, Gemini, CLI, Codex, KimiCode, and like any agent supporting the agent skills spec. And well, check out the blog post, let me know what you think. I hope you enjoy it. And of course, the link is in the show notes. On that note, folks, let's continue with today's episode. Thomas Pinder, welcome to Learning Bayesian Statistics.
Thank you. Thank you ever so much for having me on.
No, thanks for taking the time. It's late for you over there where you are, and so I definitely appreciate you being a night owl for the show and for the listeners. I'm sure they will appreciate it. I was super excited to come across your profile actually on LinkedIn when you posted actually about the GPJax integration into NumPyro. So thanks for doing that and making it public, because I don't know when I would have come across your profile. So, that's perfect. But definitely when I saw what you were working on, I became super excited, because I was like, damn, we're working on very similar topics. So it's like, great. I need to talk to this guy. We're going to have a lot in common, and I'm very probably going to learn a lot from you. So let's do that. And, you have an interesting background for sure, because you transitioned from a PhD in statistics at Lancaster in the UK, which is where you're from, and you've had senior scientist roles at mostly, if I understood correctly, only US companies, right? Big tech US companies. So Amazon, Uber, Netflix, but you're still based in Europe. So this is interesting in itself. And so, yeah, I'm just curious about your origin story, and how did your focus shift toward experimentation and causal inference in such large-scale industrial settings?
Yeah. So as you say, I did my PhD in statistics. I pretty heavily focused on Gaussian processes during my PhD. I found these to be fascinating, and the type of thing where for each new thing you learn, you stumble across 4 or 5 things which you know nothing about. So it was quite easy to fill a whole PhD learning about these things. I think I sort of got into Bayes and Gaussian processes during my master's. So actually, this was around the time when neural networks were getting pretty popular. We just had Attention Is All You Need come out. And I got very interested in the idea of adversarial detection in computer vision, and simultaneously read a wonderful paper by Yaron Gal and Zubin Garamani on Monte Carlo dropout. And I was fascinated as to whether we could combine these 2 things together and we could detect adversaries using Bayesian deep learning. And that was really my sort of pathway into the world of Bayes. It was a wonderful introduction, and I think it was really the thing which made me appreciate Bayes, like this idea of using the uncertainty to make decisions. I did work for a few UK-based companies. I did spend a little bit of time working for some startups in Lancaster on NLP, and also down in Oxford working on sort of cost-aware Bayesian optimization. But as you say, I have spent most of my career working in sort of large tech US companies. My first time was actually, I was fortunate enough to work in Amazon's supply chain team during my PhD. I got to intern with someone called James Hensman, and I was a super fun 6 months. We were basically using Gaussian processes to sort of accelerate Horvitz-Thompson estimators, so sort of approximating sums using Gaussian processes and control variates. And that for me was really what made me appreciate that actually you can do really fun, complicated, impactful machine learning and statistics in industry. Until then, I think I had this impression that you had to stay in a university to do this type of complex type of problem solving. But this was really exciting to me. However, I finished my PhD and I had spent best part of 4 years now pretty focused on Gaussian processes, and I just fancied a change. And there was an opportunity in Amazon's Prime and marketing team to go and work on some experimentation projects. So I took that opportunity, and I was sort of spent almost 3 years actually at Amazon, then working on experimentation and sort of quasi observational models, mainly working on synthetic controls. I was lucky enough to get to spend most of my time in Amazon working with Alberto Abadi, who sort of came up with the idea of synthetic controls. So that was really educational and informative for me. And I had a great time just sort of fusing together Bayesian methods with some of these more quasi-observational methods. So that's sort of what landed me in the world I sit in today.
Wow. Okay. Yeah. This is really a fascinating background and context. And those sound like a lot of really cool and interesting jobs. I think listeners will know my passion about Gaussian processes, so of course I resonate with that. I already have a few shows about Gaussian processes that I'll put into the related shows on the website. And by the way, folks, we have a completely revamped website now where each episode comes with an accompanied blog post that I write, and we have like all these key takeaways and related notes. That's being a huge effort from the team here at Learn by Stats. I've only been, leading that from the background, and now it looks really, really well. So you'll see, like when you go there, you'll see all the related shows that I'll put in there. So we'll have Gaussian processes, and probably we'll have some of the episodes we've done about state space models, because I know, Thomas, you work a lot also on these kind of models. So I'll have that in there if you want that as background for the conversation we're going to have today, because we're not going to dive too much into these technical details. But yeah, damn, sounds like super fun work, Thomas, and I understand definitely where you're coming from, and I'm really happy also, as you were saying, that now these kind of jobs are not only in academia, but also in this kind of industry setting where you get to also actually have an impact on really how things are done in a massive scale company. And I think it's really, like, that's really amazing that we can live and actually contribute at such a time, personally. So yeah. You also lead something that's called GPJax, which is an open source package, which is why I know you. And for those unfamiliar, what is the overarching big picture goal of this library, and why was Jax the necessary foundation for it? So, like, also just some info about my audience. You can assume that most people will know what a Gaussian process is and what Jax is. So feel free to build on that and answer that question.
Yeah, I might start with the second part because Jax was not a necessity for GPJax. It actually came about because during my PhD, I actually used to work on a Julia library for Gaussian processes, Gaussian processes.jl. And that was really where I learned coding, actually, was in Julia. And then through my PhD supervisor, I contributed to this library, and I really like this functional way of programming, but then I kind of realized that to get your code out there and used by people, Python is, for better or worse, the dominant language in our world. And up until JAX, I think PyTorch and TensorFlow both encouraged this kind of object-oriented way of programming. So when JAX came along, I was naturally very attracted to the framework it provided. And it honestly, GPJax started because I wanted an excuse to play around with JAX during my PhD. A nice thing about being in a university is you're allowed a large amount of sort of academic freedom. And I took that as an opportunity to just take some time to learn about how JAX worked. And at the time, I knew about GPs, and I thought, well, there's no library in GPJax in JAX for GPs, so why don't we make one? So it really did just start out as a piece of research code. And I think today it's a little bit more than a piece of research code. It's a little bit more reliable, I think. But I think the overarching principle of GPJax is to essentially provide the sort of verbs and nouns for people wanting to fit GPs in maybe a non-standard way. So I think GPyTorch and sklearn have Gaussian process implementations, which allow you to sort of fit a GP out the box and get the estimates out at the end in a reliable way. GPJax, I wasn't trying to recreate that framework in JAX. What I really wanted was something with very few guardrails and the ability for researchers to really hack around in a GP and to maybe do some of the more unorthodox things which some of these larger frameworks would prevent you doing, and allow people to basically have all of the components of a Gaussian process, and they can choose how they plan on composing those components with one another to maybe develop novel GP methodologies. So that's really, I think it's still true to that principle today. I think it still sits in that space. But that's really where GPJax came from, actually.
Okay. Yes, I can definitely resonate with the idea of just being curious about a method or a framework and just trying to find a use case for learning it. Well done on doing that. I think also the packaging itself is really helpful and useful for researcher, and I think you did a great job on that. So people, if you want to check that out, it's in the show notes. Definitely give GPJax a try if that's something you're curious about and need right now. I will also put the links to GPyTorch that you were mentioning for sure.
Yeah.
Something you also work on frequently is bridging Bayesian method. Again, something I work a lot on. So I was very interested in talking to you, especially on the
Yeah, I think Bayesian methods lend themselves very naturally into the world of causal modeling. I think when you work on these large causal questions inside of industry, I think it's very rarely a binary outcome. I think it's very rarely the case where you run an experiment, be it a randomized control or some type of observational method, and you get a very clear picture at the end which says you should definitely do this or you should definitely not do that. I think these type of business questions are often layered in nuance and complexity. And I think the role of us as scientists when we're trying to build models to address these type of questions is to really provide our stakeholders and partners in business with the context which allows them to make what they believe to be the right decision, and that should be guided by their own expertise and what the data is saying to them. And I think Bayesian methods really give you a very natural way of reasoning about the uncertainty. Like, we no longer have to worry about just getting a treatment effect. We can get a treatment effect and we can get a credible interval around that treatment effect, and we can work with the full posterior distribution if we like, and we can then start to talk about the risk of making a false positive to our stakeholders. And in my experience, when you start to frame the outcome of these causal questions through the lens of probabilities and sort of the likelihood of something being positive or the likelihood of the effect being greater than some value versus compressing things down to a p-value being significant or not, I think you provide your colleagues and your stakeholders with far more context and information that should allow them to make the best informed decision that they can off the back of the data you've modeled.
Yeah. I mean, I think you're preaching to the choir here, and I'm pretty sure everybody in the audience will appreciate what you're saying. Something I'm also obviously very curious about on your work is you've done some work, or you're actually you're at least very curious about Bayesian synthetic control. So here we're talking about quasi-experiments, methods. We haven't talked about that too much on the show, actually, weirdly, because, I mean, I think it's scattered across a lot of episodes, but we have at least that episode with Ben Vincent, the author of Causal Pi. So I will link to that show, to that episode, and of course, put in the show notes Causal Pi. But can you tell listeners what Bayesian synthetic control is about and how it works?
Yeah, so I think Ben has some excellent stuff on this in Causal Pi. Like, I would definitely recommend people go and look at that. It's truly excellent. Synthetic control, though, I guess, to me, when I first saw synthetic control, I think in its original formulation, it's essentially posed as an optimization problem where you have a collection of control units and then one or many, let's just say one treated unit for now. And your goal is to basically form some linear combination of the control units that they best match the treated unit before the intervention was applied. And in the original paper, Alberto does this by sort of optimizing the weights by constraining the weights to live on some probability simplex. And it forms it as a constrained optimization problem. However, I think when I first sort of saw this, I kind of just thought of it as linear regression in a way where my response variable is my treated unit, and my design matrix is just a collection of control units observed over time. And my Bayesian mind said, well, if I'm performing optimization on a simplex, that's somewhat analogous to just putting a Dirichlet prior down on the coefficients of my linear model. And so I just sort of implemented that using NumPyro and PyMC. These models are exceptionally easy and fast to fit nowadays. And I think what you get out of this is, I think it's a little bit more than just taking a frequentist method and saying, let's make it Bayesian because we can. I think by sort of recasting synthetic control from this constrained optimization problem to this sort of Bayesian regression problem, you give yourself a series of tools which actually allow you to perform quite a rich mode of inference. Like optimizing the weights on the simplex is somewhat fragile. Whereas when you set your Dirichlet prior, you can be selective in how you set that concentration parameter on the Dirichlet distribution. And you can then start to say whether you think a few units would be very informative of the counterfactual. And then I'm going to set a very low value for my concentration parameter. Or you might believe actually many units are explanatory of the treated unit, and you can put that concentration parameter a little bit higher. Or as I frequently did, you can put something like a gamma hyperprior down on that concentration parameter and really just let the data drive this type of sort of balancing that. And I will sort of return to this original question, this original point I made of like performing inference and giving stakeholders context around the confidence and the sort of what happened on the way to getting to your treatment effect. When you perform a sort of ordinary synthetic control and you do this optimization on the simplex, when you want to get then some uncertainty around your treatment effect in the sort of original synthetic control method, the idea was to do a permutation test. So where you would take each of your control units, sort of pretend that it was a treated unit, and then try and estimate the treatment effect and cycle through your pool of control units and then sort of measure the sort of average distance between your treatment effect and then all of these, and you would get the uncertainty. That's okay, but all you end up with is a boundary, like a permutation test interval around your treatment effect. You don't know what happened between the intervention and maybe the weeks which led up until the end of your treatment effect. Whereas when you have a linear model, a Bayesian linear model, you get this full trajectory from treatment point until final time point, and you can see how the treatment evolved over time. And you also have fewer concerns when you have very few units, like this permutation test becomes a little bit unstable. However, when you have the sort of Dirichlet prior approach, I think you end up with much more robust inference. And I think in practice, this is very meaningful because when your estimates are more reliable, you save yourself ever been in that awful position where you've given some guidance to a stakeholder about how they should interpret some causal effect, and then it turns out that actually your model was very, very fragile and you need to maybe change that narrative. I think the Bayesian approach gives you a very robust mode of inference here.
Yeah, for sure. And next, I think that was a great explanation of what synthetic control is, but basically, yeah, the idea usually is to try and find some combination of units that represent the treatment unit that you have, and basically trying to make another treatment unit, but just that wasn't treated, and to have the counterfactual as, well, if that unit had not been treated, it would have looked like that, whereas we have observed what it looks like when it's treated, so the difference is the causal effect. And like if you want an example, it could be something like, let's say, some company makes a change, some multinational company makes a change to the way they operate in Argentina because of law or something like that, and only in Argentina, but they don't change anything in the rest of South America. Then you could use some synthetic control here to try and create a synthetic Argentina based on a combination of weights from the other countries of South America that, in a way, when they are combined, gives you a sort of simile Argentina, and then the difference is your causal effect. So here, the difficulty in this method is actually in computing the weights and making sure that actually your synthetic unit is actually a good proxy of what the treatment unit would have been without the treatment. Is that correct?
It's correct as far as I understand it. Yeah. I
Okay,
think
yeah.
that's a great explanation of what it is. Yeah.
Me too, me too. But it's always weird to like, it's always a bit weird to explain these things because there is a lot of like, this is a unit. What would have been like if it wasn't treated, but it's actually treated. So you have to be extremely careful in the definitions and the word you're using.
Yeah.
And
I agree.
yeah, go
I
ahead.
think that counterfactual unit is actually like a super rich object to have in a causal
Yes.
model, right?
Mm,
It's definitely the path you get to your treatment effect by comparing sort of what happened versus what would have happened. But that counterfactual unit actually gives you so much information about like scenarios that could have
yeah.
happened. And if your control units were a different set of control units, what would that mean for your counterfactual? Like having this Bayesian synthetic control giving you this full counterfactual distribution gives you a super
Yeah.
rich object for which you can start to reason about different scenarios. And yeah, I think
Yeah.
your explanation is great. And yeah,
Mm,
that counterfactual is really, really the key part, I think.
yeah. Yeah, completely. And what's also fascinating to me in, I think, all the quasi experiments methods I know and have used is that actually computing the causal effect is super simple. It's always a difference between
Yeah.
the counterfactual unit and the treated unit. What's hard is actually getting to an estimate of the counterfactual unit. So getting there is hard, but then once you get there, it's super easy. You just compute the difference, and if you're in the Bayesian framework, you actually have a full posterior of differences, and you can make all the bells and whistles that you were talking about.
Yeah,
So
it's really like an iceberg
yeah,
type situation, right? Like the tip of the iceberg, that treatment effect is really easy to get to. Everything beneath and all the assumptions you've had to make and the modeling
yeah.
choices you've then had to translate, that's where the work goes in building these models.
Yeah, yeah, exactly. And I like that. I mean, in a way, I like that because it's a bit like Bayes. Bayes, you have one estimator, the posterior distribution, and you're done. You don't need to know about all these tests and so on. It's just like you have one estimator. And here I like that also because you have one estimator. It's just the difference. That's your causal effect. That's what you care about.
Yeah.
And you need to get there, but it's always the same thing. And I think it's great. So actually, there is a thread I could pick up here on like you talked about permutation tests and the frequentist way of doing that. I think there is like also a big limitation of that. I think when you talk about p-values, that like you're also limited to the number of units, and you cannot go below that for your significant threshold. And so that's a big limitation. Like if you have 20 units, you literally mathematically cannot have a p-value that's lower than 5%. And that can be a problem. But that's just I think it's more of a nitpick, or maybe for a debate about the more statistical conversation. And I have so many other topics that I want to talk about with you. So let's go on. Before that though, and before we talk about synthetic differences, can you just remind me quickly why using a Dirichlet distribution for the weights is actually more robust? Because I think I missed that, and I'd love you to repeat that.
Yeah, maybe let's take a step back and sort of
Mm-hmm.
like reframe it in the original synthetic control idea of optimizing on the simplex and sort of performing optimization on the simplex and sort of specifying the Dirichlet distribution. They're both essentially supplying the same geometric restriction on the coefficients of your units. And you're doing this because if you just treat it as an ordinary least squares type problem, all of your control units are really highly correlated both with each other and with the treatment unit in the pre-treatment window. So you have this multicollinearity problem, and you really need to regularize these units. And what happens in practice when you are optimizing on the Dirichlet distribution, when you're optimizing on the simplex, is you end up with very sparse weights. Like you end up with most of the control units been assigned zero mass, and then a few control units basically carrying the weight of that counterfactual distribution. And that's quite a heavy task, and it's a pretty sort of brittle estimator. And for example, if you maybe introduce an additional unit into your control set, it'll completely shift the allocation of mass across your unit, and that can then dramatically change your counterfactual distribution. And it's not to say that the Dirichlet distribution is necessarily better, but I think it's a little bit more configurable, and you can be a little bit more flexible in how you want that weight to be allocated. As I sort of said earlier, like that concentration parameter, as it gets closer to zero, will start to sort of give you much sparser units. Whereas when it gets larger, you'll then start to allocate the mass uniformly. And as a practitioner, you're totally free. If you have no idea whether you need very few units or you need quite a lot of uniform mass spread across all of your units, you're totally free to just put a prior down on that value and sort of allow the sampling routine that you pick to sort of guide you to the right value. But there's also another sort of framing here. Like I've worked on some problems in the past where actually you're sort of running like sort of experiments where putting units into either treatment or control is somewhat costly, and you maybe want the smallest design possible. Like in these cases, you really like almost want to specify that by definition, I want the smallest number of control units, which will allow me to have a well-explained counterfactual. It's quite hard for me to reason about that when I'm optimizing on the simplex, whereas when I'm putting that into my prior distribution, then I can purposefully set that concentration parameter to be quite small. So I don't think it's necessarily better. I just think it enables richer inference, and it allows you as the practitioner to have more hooks into the model to impart the information which you think is helpful in getting to your final causal estimate. And it's the classic case of there's no one right way to do this. But having more options in these type of cases is often better, and having less of a black box type model.
Sure. So I encourage people to read your blog post that I put in the show notes about this topic. Now let's turn briefly towards synthetic difference in differences. So I think diff in diff, most people will be somewhat familiar with the concept, but can you tell us a bit more about that, what it is, when to use it, and how? And I know you've done a bit of work on that lately, mostly as something you're curious about. So it's also great to pick your thoughts where, how you're thinking about that right now, and still have your thinking evolve, and not at all being, not at all prescribing things here, but actually tell us how you're thinking about that topic and how that influences your work. And of course, I will put the blog post you wrote about that in the show notes also.
Yeah. So let's just thinking about diff in diff, I sort of gave an explanation of how one can think about synthetic control as a form of linear regression. The same statement is somewhat true of diff in diff. Like in differences, you have a treatment and control unit, and you have this pre versus post intervention window, and you sort of then end up with two indicator variables, like was the unit in control or treatment, and was the unit in or was the observation in the pre or the post intervention window. And then the interaction between these two variables ends up, the coefficient on that will end up being your treatment effect. And so diff and diff and synthetic control can both be framed in the light of linear regression. And there's some really nice papers by Guido Imbens, and might even be a talk now on YouTube from Guido Imbens, sort of framing pretty much all of this line of literature as just different variants on linear regression. And it's a really great talk. So to me, if we can frame diff and diff through the lens of linear regression, then much like with synthetic control, I have the option to cast this in the light of Bayesian regression, where now my prior distribution on that indicator, on that interaction term, is the sort of prior on my treatment effect. And that's kind of nice. Synthetic diff and diff was a paper from maybe 5 or 6 years ago now. I think it was 2019, actually. But it essentially said, well, what if we can combine together diff and diff with synthetic control? Meaning synthetic control gives me a way of assigning a collection of control units to explain the counterfactual. And diff and diff sort of allows me to weight my pre and post intervention windows and have sort of weights on that. Synthetic diff and diff says, what if I could have weights on time and on the control units? And it goes about estimating them in sort of like a 3-step process, where I first would learn the weights of the control units using all of the pre-intervention data. And then I would go about learning the time weights using only the control units. And then, as you put it earlier, then we just get the treatment effect out at the end by just doing a differencing between two terms. However, the challenge in trying to cast this into the light of Bayesian inference is now that I sort of have this information restriction where I have all of my data, pre and post control and treatment. However, I have sort of two quantities I need to estimate, the unit weights and the time weights, but the unit weights can only take data from pre-intervention, and the time weights can only take data from the controls. And so in a Bayesian framework, normally like your likelihood would just factorize out over the data. However, I can't do that here. Otherwise, I'll have information about the wrong quantity flowing into the wrong component of my model. I actually just stumbled across this idea of sort of a cut posterior or modular posteriors just in passing. And this essentially says, like, in networks, you may have this problem quite commonly where you want information to flow to different components of your posterior and then sort of compose together these modules into one full posterior distribution. And I kind of thought that, and I saw that, and thought maybe we can apply that to synthetic DID, and it turns out you can actually relatively simply. I have a sort of very short ideas on my blog about how you could do this, and it's very recent and could very well be wrong. So I would encourage people to read it with a skeptical eye. However, it turns out that when you sort of frame Bayesian synthetic diff and diff in this cut posterior type way, you end up with an estimate which is very comparable to the estimate reported in the synthetic diff and diff paper, which essentially said synthetic controls on their own overestimate the magnitude of the treatment effect from the original problem of the California smoking example. So this was a sort of the data set used in the original synthetic control paper, which measured the sort of effect of cigarette ban in California, where California was the treated unit and then all the other states became the control units. And I think the effect in that paper was around 26 sales of cigarettes. And actually, synthetic diff and diff estimates this result to be closer to minus 15 packs per capita. Bayesian synthetic control, synthetic diff and diff, recovers that almost exact same estimate. It gets around minus 15.6, so a 0.6 difference. But you get the full posterior out, as we said multiple times. This sort of gives you that richer form of inference. And yeah, I'm still sort of pushing the idea around this sort of open questions around sort of like how do you represent the uncertainty on that treatment unit itself, because you have sort of time now factoring in. And there's sort of different ways you can parameterize the model such that it becomes closer to synthetic control and closer to diff and diff, or in certain cases equal to those models. And I'm still trying to sort of mull over what that means. But it's quite interesting, and it's something I'm quite excited to sort of continue developing and seeing how that idea evolves.
Yeah, this is a very, very intriguing and I think powerful idea of merging synthetic control and diff and diff. Honestly, I had not heard about that before preparing the show. So yeah, thanks for putting that in front of me. I will definitely look into that and see, like study it as you're doing right now, and see how we can use that actually in a professional setting. And actually, if you can you add the YouTube video of the talk you mentioned to the show notes, because I think it's going to be very helpful, especially if it's exposing this idea of synthetic diff and diff.
Yeah, let me try and find the talk.
You can do that after the show.
I'll add it to the show notes.
Yeah, exactly. Awesome. And so that was for the quasi-experimental causal inference part of the episode for today. We can get back to that at some point if you want, but I also want to ask you about GPJax, because, well, that's another common passion of ours. So you gave us already the elevator pitch for it at the beginning, but when, like more precisely, when would you recommend listeners to use it and how?
I lost the last part of my question then. You said, when would you recommend listeners to use it? And then I lost you.
And how to use it, like usually what's your workflow when you're using GPJax?
Got you. Yeah, how? Yeah, so GPJax is definitely not the Gaussian process you should use all the time. Like GPJax will let you do some things which are a bad idea. And other frameworks will have guardrails in place which will just stop you doing that. And I think if you're, for example, if you want to put a Gaussian process into a production system, and it's a very high stakes type scenario, I think maybe using GPyTorch is perhaps maybe a safer choice. I think it simply has more guardrails put in place. Equally, I think if you really don't care too much about the model's construction and you just want to fit a Gaussian process, I think something like and you don't have very big data, then I think something like sklearn will allow you to fit a correct Gaussian process in far fewer lines than what we would require you to use in GPJax. So I think those are the two cases where you maybe wouldn't want to use GPJax. However, I think if you're a researcher and you're wanting to fit maybe unusual Gaussian processes, so one example would be if you have a different type of kernel which allows your covariance matrix to have some type of unique structure which you wish to exploit when doing the matrix inverse, the common bottleneck in all Gaussian processes. GPJax gives you super easy ways to hook into that. Or if you have a new variational approximation which you want to test out to accelerate a variational inference type workflow, then again, GPJax makes that really easy for you to do. So I think in these type of cases, using GPJax is a great idea. I also think if you really want to fit a model and then retrospectively decompose it, dig into it, take it apart, I think and or compose it with other modules like a linear component, like a linear model or something else, then I think GPJax enables that very nicely. Like as you mentioned in the introduction, we integrated it very tightly with NumPyro, which allows you to build much bigger Bayesian models with Gaussian process components therein. And I think in these type of cases, I think GPJax is somewhat unique in the sense that it really does allow you to build quite complicated models with relatively little code. As to exactly how I use GPJax, I actually use it less these days. I find myself using Gaussian processes less and less these days and find myself working on GPJax as a hobby. I tend to use GPJax in a Marimo notebook, and most of the time these days I find myself fitting Gaussian processes for case studies and for trying to understand some data. I was never the best methodological or theoretical researcher during my PhD. That was never my strong suit. I think where I was able to sort of be most useful was in building tools and like GPJax and sort of working on causal problems, which are much more closely coupled with applications. So I don't find myself sort of developing too much novel methodology. I prefer to let other people develop clever methodology, and then I would work out a way to provide a nice abstraction for that within GPJax. It would allow people to use this nice methodologies within the GPJax framework.
Okay, yeah. That makes sense, and everything you've talked about here also resonate with my experience of Gaussian processes, especially the fact that they're very modular, that you can combine them with other kind of models, that you can have that in, like, yeah, you can have a Gaussian process component or even several Gaussian processes components in a model that has also linear regression components. It's just, yeah, that's one of the big powers of Gaussian processes is that one, and that's why I also one of the big reason I love them so much. One thing I'm curious about though is that, you know, when scaling Gaussian processes, what were the primary software bottlenecks that you encountered in the Python ecosystem that led you to favor the JAX stack we talked about at the beginning? That was more of a curiosity, but also now you have the NumPyro stack integrated into GPJax.
Yeah. So I think although I opted to use JAX at the start, I think really I had actually before that implemented a very, very small Gaussian process library using like NumPy. And really like JAX solves so many problems where you have to calculate, you don't have to worry about calculating the gradients. Like in the Julia package, we had to calculate a lot of the gradients by scratch, which means things are super fast, but for each new kernel you want to introduce, you have to calculate the gradient with respect to each of the parameters of that kernel, and it's very difficult. So I think software like JAX really unlocks the ability to build out new code very quickly, because I can take a derivative with any leaf of my pi tree, and that's a super powerful paradigm that I can sort of, through the chain rule, just essentially differentiate through my whole loss function in each of the parameters and get out a gradient at the end. And within JAX also, and now PyTorch and TensorFlow, I can JIT compile my whole graph, which in, again, something like a Gaussian process where computation can be quite heavy. JAX really solves that problem of making a highly computationally challenging problem slightly less challenging through the ability to JIT compile your code. On the NumPyro side, NumPyro really solves the problem of, as you said, like integrating a Gaussian process into a wider framework, because NumPyro is a lot more general than GPJax. Like NumPyro simply provides a way for me to build any type of probabilistic model. There's nothing to say we couldn't support that in GPJax, but we're not a probabilistic programming library. We're a Gaussian process library. And this has really been the paradigm I have had from the start, where GPJax will fit Gaussian processes. And then when there are good libraries for us to offload other functionality into, we'll always take that. So for example, we don't implement any optimizers inside GPJax because there's an excellent library called Optax that can achieve optimization. So we write software within GPJax, which allows us to hook into Optax and allow Optax to maintain an excellent optimization library. That statement is true for NumPyro and the sampling. Like, there would be nothing stopping us integrating a Hamiltonian Monte Carlo sampler into GPJax. In fact, we did that using the Julia library before. However, you then have to start maintaining a Monte Carlo or an MCMC sampler as well as your Gaussian process code, and that becomes challenging. And to be totally honest, like, I can write a good piece of code to implement a Gaussian process, but I am not necessarily very well skilled in writing the best sampling library, whereas NumPyro does provide a really efficient sampling library. So I think it's really identifying dependencies and sort of codependent libraries where you can offload challenging functionality into these libraries. And GPJax has always been designed to kind of allow us to connect with other libraries as easily as possible and sort of share the strengths of several libraries therein.
Yeah, that makes a ton of sense. Much better to stand on the shoulders of giants than just re-implementing everything on your own, and just playing on our strength, as you were saying, where you're a very good tool builder, and so basically you have that ability to use different tools and blend them and make life easier for people who need that kind of models. I think this is amazing, and that's also really the spirit of this show, because again, I resonate a lot with your profiling experience. So yeah, for sure, I completely understand where we're coming from. Something you've somewhat talked about already a bit, but I'm curious to hear if you have more to say, is what are practical ways you use GPs and maybe even GPJax in your work in relation with causal inference?
Yeah, so we use some. So I use Gaussian processes typically if I need to fit some type of regression model, and I just kind of want something that's going to work, and I don't want to have to think too much about it, and I really care about the uncertainty. I'll often reach for a Gaussian process. there's an element of personal bias. It's a model I simply know how to fit relatively well. And when linear regression doesn't solve a problem, I know there are other like tree-based methods, and there are several other different approaches I could reach for, but Gaussian processes are simply the tool I have. So they are sort of my default regression model. I think we've used them quite a lot. I had a unsuccessful attempt at using Gaussian processes for Bayesian synthetic diff and diff whilst at Amazon. So there I had this idea of basically saying in synthetic control, your weights belong to this Dirichlet distribution, and I want to essentially correlate my weights in time. So kind of tried to place Gaussian process priors down on like the concentration parameter and try and evolve that parameter through time. And then, or I also tried trying to evolve the weights through time. But the inference just became a bit of a nightmare, and like the inference was super unstable. R hats were all over the place. The model was really not a great model, and I never was able to get it to work very well. But although the model was unsuccessful, I think it does speak to where Gaussian processes can be useful in sort of causal inference workflows and just generally in industrial workflows. When you have this sort of latent property which you wish to propagate over time or over some spatial domain, I think it can be really useful. I worked a little bit on some spatial data before where we essentially needed to sort of model a spatial residual between two satellites. In this type of instance, like the satellites were measured on different resolutions. Like one of them was on 9 by 9 kilometer grid cells, and one of them was on 500 by 500 meter grid cells. You kind of then need to propagate this residual and spatially smooth it. In these type of instances, like a Gaussian process is a really natural type of model, I think. So I think it's like anything. I don't think they are the silver bullet. I don't think a Gaussian process is the model to be used every single time. But I think in these cases where you really care about propagating uncertainty around a model and you really want to sort of carry information through a model and never compress information down, I think Gaussian processes, in my experience, often allow you to achieve that relatively easily.
Yeah, yeah. Same experience here where these kind of models where you need nonlinear relationships. You don't really know what they look like mathematically, don't really have the time and expertise to do that, and want a method that's going to work. GPs are going to be a great bet. As you were saying, for spatial data, for sure. Also, me, have used them a lot for time series data. Again, recommend them a lot for that. So yeah, like all that thing is extremely, like, they are extremely versatile and now pretty easy to fit, honestly, to sample with the stacks we have. So unless you have huge amount of data, but now it's so much easier to sample GPs than it used to be.
Yeah, I even think actually nowadays, even unless your data set is truly huge and high dimensional, I actually think high dimensional hurts you more nowadays than high number of observations in a Gaussian process. I think with a lot of these stochastic sort of inducing point type ideas and the Hilbert space approximations that we have for GPs, I think we kind of moved away a little bit now from this idea that GPs don't scale. I think they do scale in the number of observations. I think the challenge is still scaling in a high number of covariates. And this is still where I would be inclined to reach for some type of tree-based model. However, yeah, they are pretty easy to fit nowadays. I agree.
Yeah, no, exactly. And I mean, if people are actually interested in seeing what you can get from Gaussian processes, I will put in the show notes the project I have still ongoing with Max Goebel, who was on the show. I will also link to his episode in the related episodes on your episode's show notes, Thomas. But yeah, like for that project, that's called the soccer factor model. We used a bunch of hierarchical GPs on different timescale for soccer strikers to try and predict the number of goals they would score in their next game. And so yeah, like if you go to this dashboard, you'll see the depth of analysis you can get from these kind of models. And this is, yeah, this is always, to me, this is thanks to such powerful models. And so yeah, like this is an open source project, so that's great because we can show everything. So you can go in there, there's a paper, there's the code that's available, the data, everything in there. It's if you want to learn GPs.
Yeah, I'm not aware of this work. That sounds super interesting. We actually did something I think not too different. Well, we sort of developed a new sort of hierarchical sparse Gaussian process. We weren't applying it to anything as fun as football players and strikers' goal rates, but we were trying to sort of model different climate models, and sort of in the climate science world, there's these projections of sort of surface level temperature out to sort of 2100. And different models, of course, produce different predictions, and under different constraints, you end up with different predictions. And we were actually trying to do something pretty similar to what you described, where we were putting hierarchical Gaussian process down on this to kind of understand the latent underlying sort of trajectory which underpinned all of these models in a way to kind of ensemble them, but also allow each model to vary from one another. So yeah, maybe
Yeah.
we should compare approaches. Maybe there's something interesting happening at the intersection.
Yeah, for sure. Happy to share notes. But yeah, that sounds a lot like what we've done. And also, I think in your case, it's the same. In our case, that was very clear that the hierarchical structure of the data, was helpful because we have players, but they are part of teams, and even players are just part of a special population. So that was something that was really important to us, to have that kind of higher level population GP, and that would trickle down towards each player who would have his own GP that would vary from the population level one, but would still have the information from the population. What is great with that is that then you can make a better prediction of out-of-sample players, like young players or players who come from a new league, from another league, and they are completely new, let's say, to the Premier League. Then you can still make a decent prediction, whereas before you were more or less flying blind. So this is very important.
Yeah. Do you also have incomplete data? Because this is something we had to grapple with. Like, not every satellite provided
Yeah.
reliable predictions at every single point in the world. Some of the models
Yeah.
were better at different points in the world. Do you have the same thing with your soccer players, where I guess not every player will play every game in a season,
Yeah.
so you end up with kind of incomplete data? Is that also the
Yeah,
case?
exactly. Yeah.
Yeah.
So Max knows the data set by heart because he's the one who who like literally made it from nothing. But I am very certain that yes, we have players like that where they get injured, or they just, like, you have a lot of replacement level player or even average player, which they just get out of the bench, they don't start all the time, then don't enter the game all the time. And that's where also having the hierarchical structure helps a lot, because, well, having predictors also, it's a combination of having predictors that gives you information about who the player is, and also having the hierarchical structure that then fills in those missing data points.
Yeah.
Um,
Super interesting.
Yeah, this is a very fun project that actually we've been doing for almost 2 years now, but it's just like it
Oh.
keeps on giving. It's such a big project and also a fun playground that you can always find something new to keep pushing the boundary. So yeah, it's part of one of these fun projects.
Yeah.
So to close up on GPJax, and then I want to touch on another project of yours, because you do a lot of things, Thomas. But so just curious about the coming roadmap for the coming month for GPJax. Do you have any priorities already, that things you want to touch on?
Yeah. So yeah, it's possible that I follow the literature less closely these days. Now I'm not in an academic setting, but my observation is the sort of literature around GPs is quietened a little bit from where we were several years ago. So I, when I look forward, at least for the remainder of this year, I'm not imagining implementing any new methodologies into GPJax. we have a pretty wide range of kernels, at least the major kernels. And our goal is not to implement every single kernel. Our goal is to provide the infrastructure which would allow someone to implement their own kernel very quickly. So we have that, and we have a couple of different variational approximations which one could use depending on their use case. And we also have a few different inducing point schemes and multi-output Gaussian processes implemented. So I think we have a pretty complete set of functionality within GPJax. So I think when I look forward to the remainder of this year, I think I want to do two things with GPJax. I would quite like to close that bridge between GPJax and something like sklearn or gPyTorch, essentially providing a higher level abstraction of GPJax, which would allow someone to fit a Gaussian process in a few lines of code versus the sort of 20 lines of code we make you write today. Using something like providing just a YAML file or just a JSON config and then building your model and fitting it. Because whilst the original use case of GPJax was for researchers, I acknowledge that many people, and myself included, sometimes just want to fit a GP. I don't want to define all of the boilerplate code every time. And also when I fit a GP, I want things like logging to be implemented under the hood. I want things like to connect to AWS or some cloud-based system. Like all of these things can be handled behind the scene very sort of easily. And I think I would like to provide this abstraction within GPJax, or maybe in a sort of secondary library. I'm not entirely sure at this point, but essentially giving people a more production-ready form of using GPJax. The other thing is I would really like to improve the quality of our documentation. So I think we've done a pretty good job with our documentation. We've made a conscious effort always to explain the underlying maths as well as what the code is doing. However, most of our examples use simulated or synthetic data, and I think we could make them far more interesting by just using real data. We had a collaborator, actually we had two collaborators, I should say, a few years ago now, who implemented a really, really cool notebook to GPJax modeling vectors. So rather than predicting a scalar value, you're actually predicting a vector. And they use this to model ocean currents using GPJax, so modeling the spatial vector field. And you can do this using a certain type of kernel. And I think this is a really cool notebook. Like, it's great. It uses real data, and it's a real problem which people actually work on. So I would like to migrate some of the GPJax examples away from using simulated data and to bring in some new data sets which are interesting and may just catch the interest of people browsing with documentation. And they might look at it and think, oh, I have a very similar problem to that. First, this is today sort of building a data set by composing a sinusoidal function and a sort of bit of white noise together, going a little bit beyond that. And to be honest, where I am now, like, those are the type of documentation, those are the bits of documentation which I enjoy writing as well. Like, Claude Code and Cursor are so good now, they can implement most of the back-end type code far quicker than I ever could with fewer bugs. But I don't think it's very good still at writing documentation and writing case studies. I think there's still a handcrafted narrative which is better than what an LLM can generate for us. And I still find enjoyment in writing these types of things. So I think this year those are the two sort of angles which I would like to steer GPJax in.
Yeah. Makes sense. And yeah, I kind of have the same experience where I feel if I can delegate a lot of the coding to the agent and just basically supervise its work, and basically doing what I've done a lot on the privacy side, where you review pull requests. Basically here you have your your agent making, like, writing the code and so on, and then pinging you for a pull request. You review that goes much faster. And then I get to go to the most enjoyable part, which is, okay, how do I use actually that code? How do I show people how to use that? How do I, basically teach people where and when and why this is useful, and writing this kind of pedagogical content where, yes, I think we as humans still have a much more interesting viewpoint, because I think we're more aware of the difficulties we have when we learn this. This is actually something we enjoy more, and that's mostly what's really, really useful to people, because most users are introduced to a software not through the code on GitHub, but through the example notebooks on the documentation website. So yeah, that makes sense to invest a lot of time in there. And actually, this notebook also, if you have it already ready to share with people, please feel free to add it to the show notes. I think this is going to be very helpful.
Sure. Yeah, will do.
Awesome. So now I'm going to start to close us up, because it's going to be too late for you, Thomas. But I do want to talk about Impulso. That's one of your new projects. And again, this, like, the resemblance is uncanny, because this is one of our common passion too. This is a package to do vector autoregression in Python, in PyMC even. So yeah, I of course looked into it before the show, but can you give us the elevator pitch, what this is about, why did you even do that, and what is the state of this project?
Yeah, so Impulso is a play on the impulse response function, which is a incredibly useful property you get out of structural VAR models. So a VAR model is essentially a way of modeling a time series model with a vector of outputs, and acknowledging that there may be correlation between those outputs. Structural VAR is something which, to be totally honest, I'm not an expert in structural VARs. I worked on them with a colleague whilst at Amazon and found them fascinating, the use cases of them. And since then have just taken an active interest in reading about them and trying to learn more about them. And I feel like I have a moderate understanding of the principles, and really it was a case of trying to use them. But there wasn't really a reliable, good implementation of them that I could find in Python, which would allow me to fit them in a Bayesian manner. I think there's some excellent R packages, but I'm not the person who can write good R code for you. And so I thought, let's try and implement something in Python to solve this problem. So it also came about because of actually what I just touched on with the use of LLMs. So I use LLMs and Claude Code, namely within GPJax nowadays, and it's pretty good. But I have a huge bias in the sense that I wrote or reviewed every single line of GPJax, so I know when the LLM is doing something weird or is in the wrong area. I was really curious how we could build software libraries from the ground up using LLMs. So I thought Impulso was a great opportunity to try out that and to try and document my learnings as we go about how we can use LLMs to build software libraries, because we will always need new software libraries, and I think it's super important that we continue to fill gaps in the ecosystem with new libraries. And so I was curious how we could leverage LLMs to achieve that most effectively. So actually, I guess the summary there is Impulso is a entirely selfish project where I've used it to learn more about VAR models and structural VAR models, and also how we can use LLMs to build code libraries.
Yeah, okay, that makes a ton of sense to me. Basically, you were curious about these models and you were looking for a toy project. And again, this is what I do all the time. So I'm like really impressed by the resemblance here. But yeah, like, and I have to say, I looked around the project. I also sent it to one of my friends, Jesse Grabowski, who is actually the person who introduced me the most to state space models. So I all the math I know about state space models to Jesse, who is always extremely patient with me and my misunderstandings of matrix algebra. So Jesse was on the show, episode 124, to talk exactly about state space models, especially his brainchild, which is the sub-package in PyMC extras to do state space models with PyMC. So you can do VAR with that, so vector autoregressions, although we do it a bit differently on PyMC extras because we do it from the state space equation point of view. So with Kalman filters, if I understood correctly, and Impulso, you do that from the linear regression equation point of view. So a good thing of that is that it's going to be much faster to sample your way of doing it because it's a linear regression. So to give listeners an idea, that's going to be a bit more like something like Profit. If you're used to these kind of packages, this is going to be something like more of that structure, whereas the Kalman filter thing is what we implemented in PyMC extras, which is going to be taking more time to sample, but you can do all the other state space model stuff. So, always trade-offs. So people curious about these models, I really encourage you to take a look at Impulso. I think the different documentation is really well done, and yeah, it's also like you're still developing the project. So of course it's still a developing project, but if you want to also give Thomas a hand, feel free to do so. Open issues, open pull requests. As an open source developer, I always appreciate those. So I'm sure Thomas will. And also, you can check out PyMC extras. I'll put that in the show notes, and related episode, the one with Jesse. And finally, Jesse and I taught a tutorial last September in PyData Berlin, introducing the PyMC extras state space submodule. So if you want to have an introduction to that, I encourage you to check out the show notes. I'll put that in there. That's called the Beginner's Guide to State Space Modeling. On that note, Thomas, anything else you want to add about Impulso, or did we summarize it well?
No, I think you gave an excellent summary. I would maybe add that obviously there is the back-end difference you mentioned between Impulso and PyMC extras. I think also PyMC extras state space library definitely tries to give you more flexibility, much like I described with GPJax, like allows you to sort of compose things together and gives you a lot of control. That's actually not the problem I'm trying to solve in Impulso. Like I'm sort of building software here maybe for economists who just want to sort of fit these models and get access to the inference from the model, and worry less about the sort of mechanics of the model itself. It's more of a high level abstraction. So yeah, they might do different things on the back end, but I think they also maybe will end up trying to do different things on the front end as well.
Right. Yeah. They probably optimize for a different kind of population. I think the state space submodule, is made to be self-contained in a way if you're using PyMC, but it's still like you're still in a probabilistic programming language environment, so you can go and combine elements together and have structural time series and things like that. I think Impulso, from what I saw, is more opinionated, and I think that's what you were going for, because that way users have to make less choices, and like often some kind of users will prefer that, some others won't. So yeah, like it's great to have this diversity in there. Do you still have, let's say, 5-10 more minutes so that I can ask you 2 other questions before asking you the last 2 questions, or should I cut to the last 2 questions already?
No, I can hang around.
Okay, so thanks for taking the time. I was actually curious, just you've worked a lot in industrial settings, so something I really want to ask you is, how do you balance the computational overhead of Bayesian sampling with the latency requirements of production level decision making?
Yeah. So I guess so oftentimes my work is I've never really worked too close to the edge in terms of having to give model inferences in the sort of milliseconds. Like often for me, the limiting factor has not been the inference speed of a model, but more the decision-making speed of an individual human stakeholder and the ability for them to digest information. So oftentimes we would run a campaign and we would get the results, and then we would have a few days to analyze them. So there, the the models are never taking more than a few hours to fit, and really then you have a couple of days to digest the outcomes and work out how to report it. So rarely have I been in that case, but I think even within there, there's SLAs or like service level agreements that your model should sit with when it sits in a production system. And I think actually Bayesian models nowadays, I think with PyMC and NumPyro and the different samplers we have, it's not they're often slower than the Frequentis counterparts, but honestly, they're not so slow nowadays. Like we're not always talking about several hours or days to fit. Like if your model is correctly framed and the priors are reasonable and the likelihood is a good choice, like they'll often fit actually quite quickly. And when they're fitting very slowly, like sometimes that's actually an artifact of your model and you've got a ill-posed model and it's simply slow to sample because it's difficult to do the sampling routine itself because you've maybe specified a bad likelihood. However, they are always slower. And I think in those cases, like in the past, when I've had real high service level agreements and we've had to give as quick as possible inferences, in those cases, I've actually ended up using things like conformal prediction. So taking Frequentis models and then trying to get some type of prediction interval on top using conformal prediction type approaches, which are super fast. Often in their simplest form, they're just a case of taking some predefined quantiles and applying them to your predictions. So those can be an option when you're really pinched for time. It would also say though, sometimes working backwards from the constraint you have is a sensible approach. So when I used to work in the supply chain team of Amazon and we used to have to deliver predictions within 12 hours, we actually framed that as saying like, what can we do within 12 hours to guarantee the fastest possible model? So that means you can't evaluate every single data point maybe in your training set. So actually building secondary models which select the data points of most information, kind of like in active learning, and putting those into your model and fitting your model on the most informative data points, and then you can get onto 12 hours. So sometimes they're just constraints you have to work around. Like in this particular model we were fitting in the supply chain, we actually really needed a posterior distribution. There was no way around it. So there it was a case of sort of working backwards from that and working out what the best you can do within the time you have. Yeah, I guess what I'm saying is there's no sort of universal answer, but Bayesian methods are not as slow as they once were, and often there are ways to accelerate them when you really need to.
Yeah, I mean, I couldn't have said it better. The thing is, I wanted you to say it because otherwise I sound like, like a preacher, and that's less objective. But yeah, like I mean, it's also been my experience where now I very rarely am convinced that you cannot use a Bayesian model if you want one. I've actually never seen that really in all the different models I've shipped in industry. It's always been, well, no, we can make that model better. And as you were saying, most of the time it's, well, actually there is an overparameterization, or the priors are too wide, or they are too narrow. Well, we can use also the latest NetPy sampler, and we can use this approximation of a GP here. Let's use HSGP instead of a plain vanilla GP. All that stuff, and then you end up sampling huge hierarchical Gaussian processes with a lot of data points on your laptop in like 15 minutes. Well, that's very, very fine, especially if you don't need to run that model every day. And if you needed to, that's 15 minutes. So it's also super fast.
Yes, I agree. Yes, totally agree.
So yeah, I mean, but this is already like such a great point, right? Because I remember when I was starting this podcast in 2019, that was a huge point of contention, not necessarily from academia and practitioners, but like in people who did know about Bayesian stats, who would still have these preconceived notion that it's most of the time the best theoretically, but impractical to apply. So let's not even try. And now I feel like this battle has pretty much been won when it comes to education most of the time.
I agree. And I think with scaling of GPUs, scaling of the quality of CPUs available to us,
Yeah,
I think data sets might get bigger, but I don't think GPUs in their vanilla form are a particularly bad case of cubic scaling and the number of data points, but often giving more compute or throwing more compute at a problem can solve a lot of your problems very quickly if you have the
yeah.
resources to do so.
When it comes to that, because it's like, oh, GPU, this is not such a big model.
Yes, that's a good point. Yeah.
That's an easy one, but yeah. And actually, given your experience and your work on these scalable Bayesian tools, I'm wondering how optimistic you are that these methods will soon become the default choice for causal inference in the industry.
It's quite a good. Yeah, that's a good question. I'm not sure they'll ever be. I'm not sure they'll ever be the default choice, and maybe that's okay. There are some. It's my belief that when we report treatment effects, we should be talking about the uncertainty that comes through a posterior distribution. But there are other fine ways of doing this. I actually often don't think they lead to the wrong outcome. I think they're often just more work to get to that same outcome. So I think there are pretty popular frameworks which can achieve pretty good results. Like I think the double ML framework in certain instances can be quite an effective tool. I think it's often used as the default choice when maybe we could look to other models to achieve what double ML can do for us. But I think there'll always be other tools. I think though I think as we evolve as an industry to continue using causal inference to really provide data points around high sort of value or high risk decision making in industry, because it's still not the norm, I don't think. I think we are still working towards a world where everyone is doing that. But I think as we continue to do that, I think the need for Bayesian methods becomes pronounced, not because we as Bayesian practitioners believe them to be the right model to use, but actually because the guidance we're getting from our stakeholders will mean the only model that is really reasonable to use is a Bayesian model. For example, when I've worked on some sort of geo testing and sort of video marketing projects in the past, like our stakeholders really wanted to know questions like, well, what's the probability, like what's the risk of us making the wrong decision here? And like, can you put dollar values on that? That's really quite easy to do when you have access to the posterior distribution. But if you're trying to do that through the lens of p-values or confidence intervals, that's actually quite challenging. And so I think it may end up being more commonly used because we end up being more risk-inclined or risk-minded when we start making these decisions as we as an industry evolve to using these models more for our sort of decision making.
Yeah. I agree, and I think that was kind of a provoking question on my end, and I completely agree with you that actually the assumption of the question was that Bayesian stats would somehow need to become the default. I don't think they do, but I do think that they need to be more basically accepted out of the box as something in the toolbox. And basically, like just as you're using scikit-learn or PyTorch or any other framework which looks classic to any member of the team, then when it's needed, well, you're using a Bayesian causal inference method because that's what solves the problem best, and you don't have to overly justify why. And like you just justify it as you would using a neural network or an LLM for some other project. And I think that's definitely what we're trying to build ourselves to, which is where, definitely it makes sense. Let's just use that and we're good. And then we're going to have all the bells and whistles. And I'm also very, very sure that when people start to see you don't need to know what a p-value is and you can actually interpret the confidence intervals as you actually want them to interpret, this will become one of the beloved methods of statistical folks for sure.
Yes, I totally agree on that point. I do also think just picking up on something you just said there, I think there's also an element of we sort of need to own our own shortcomings here. I think like scikit-learn and other tools have done an amazing job about making frequentist type methods super accessible. And to be completely honest, we as the Bayesian community have not done such a good job. A lot of our packages and a lot of our frameworks are very much geared towards researchers or people wishing to fit new Bayesian models. And I think there are libraries like PyMC and a NumPyro and sort of what I'm trying to do with Impulso to try and bridge that gap. But we really haven't designed an ecosystem which makes it particularly friendly for people who don't already understand a lot about Bayesian methods to just go and fit a Bayesian method off the shelf. So I think there's an element of we also need to continue to build the right tools which will allow Bayesian methods to become a more default option within a practitioner's toolbox.
Yeah, 100% agree. Awesome. Well, Thomas, I could continue this conversation, but you're gonna have to go to bed at some point. So I'm gonna let you because I'm that magnanimous. But before that, before letting you go, I'm gonna ask you the last two questions I ask every guest at the end of the show. First one: if you had unlimited time and resources, which problem would you try to solve?
So yeah, I mean, there are huge problems in the world, and most of them I'm grossly incapable of solving. But I think a big problem which I would love to, if I had unlimited time and resources to try and solve, would be the supply chain issue that we have in the world. Like the brittleness and the fragility of supply chains feels like a problem which I could imagine working on. But it's incredibly complex getting data around like where weak points in supply chains sit and trying to model them using Bayesian methods would be incredibly meaningful and incredibly impactful, but incredibly costly both in terms of time, money, and resources. But if you're telling me I have unlimited time and resources, I think that would be the problem I would spend a lot of time thinking about. How do we build more resilient supply chains, and how do we understand the risk of supply chain problems?
Yeah, that makes sense for sure. And then second question is, if you could have dinner with any great scientific mind, dead, alive, or fictional, who would it be?
It would be amazing to have dinner with Radford Neal, actually. I always find Radford Neal's papers incredibly conversationally written whilst also being highly academically stimulating and informative. I could imagine he'd be an incredibly interesting person to have dinner with. And really for me, when I was first getting into the world of Bayesian statistics, some of his papers on connecting Gaussian processes to infinitely wide neural networks and Hamiltonian Monte Carlo, and a lot of these type of papers, honestly, for me, were so accessible whilst also being so dense in information that I would keep reading them and coming back to them. It'd be amazing to sit down with Radford Neal and try and learn some of the things which he has in his head.
Yeah, I love that. And I think you're the first one to answer that on the show. So that's not the goal. The goal is to sample the distribution, but you're definitely on the tail for now.
Okay.
Awesome. Well, Thomas, let's call it a show. That was an absolute pleasure to have you on. Thank you for staying up for us. I'm sure everybody appreciates it. And well, listeners, if you want to give Thomas a token of appreciation for his work, definitely drop him a word on, wherever you go, LinkedIn or GitHub if you're using any of his project, or if you have ideas on how to contribute or just want to start on open source and think that one of Thomas's project is something you want to contribute to, then just chime in on the GitHub repo, and I'm sure he'll be very happy. On that note, Thomas, thank you so much for taking the time and being on this show.
Thank you ever so much for having me. It's been a really fun conversation. I couldn't have thought of a better way to spend my evening.
Well, I am very glad to hear that. This has been another episode of Learning Bayesian Statistics. Be sure to rate, review, and follow the show on your favorite podcatcher, and visit learnbasedstats.com for more resources about today's topics, as well as access to more episodes to help you reach true Bayesian state of mind. That's learnbasedstats.com. Our theme music is Good Bayesian by Baba Brinkman, feat. MC Lars and Megaran. Check out his awesome work at bababrinkman.com. I'm your host, Alex Andorra. You can follow me on Twitter at Alex_Andorra, like the country. You can support the show and unlock exclusive benefits by visiting patreon.com/learnbasedstats. Thank you so much for listening and for your support. You're truly a
good Bayesian. Change your predictions after taking information in. And if you're thinking I'll be less than amazing, let's adjust those expectations. Let me show you how to be a good Bayesian. Change calculations after taking fresh data in. Those predictions that your brain is making, let's get them on a solid foundation.